Thank you. Hello, everyone. Welcome to another edition of Learning Glass Studio. Today we'll talk about some financial stuff that is relevant to everything, including engineering design. So it's about concepts of cash flow analysis considering the time value of money. So discounted means that you're accounting for the fact that due to many factors, a number you put on the amount of money depends on whether it's in the future or in the past. One example that we may be familiar with is the compound interest formula, which is based on the concept that if you make someone a loan or a business, a firm makes a loan to you, it's subject to this commonly universally applied concept of interest, that both just a business and even smaller scale transactions operate on the principle that if you have a certain loan, it's going to be tied to interest, and which is tied to time. So this is the final amount, the final cost of the loan, which would be another way to think about it, as we'll say, it's the future value of this loan. Then the principal is how much is first transacted, what the actual loan is, but then another way to think about it is it's the amount that gets transacted right now. And businesses operate, this is one of the bank's money makers, is that it's a universally applied principle that whenever you have this type of loan, this type of transaction, the incentive for the business or even some people is that they're going to gain some interest, some rate, where this money accumulates another cost that goes to the loaner. And that's at a given rate. It's an interest rate. And we are going to learn that this goes in both directions, that what we're saying is that because of this interest rate applied to the principal, you're going to have a higher cost at the end. It's some rate that's added to one. So it's some amount that it's going to grow to contribute to the final amount. So of course it's related to time, but more generally you can just say this time can be the months, days, or years. So it's the number of times you apply this interest. So if it's monthly, then it's 12 per year. And you'll get a much different result if you apply this every month. It'll just grow so much faster than if you apply this every year. So both the rate and the number of times you apply it affect the final number at the end. So this is a universally applied principle, and we might be familiar with it already. But we can also do this in reverse. We can say that assuming that I have some future value that I can expect that is known, the question is, how much is it worth to me today? So you do that for many reasons. It's all based on decision making, because if you want to try to gauge on what direction to take your business in, for example, or whether to do a certain project to make money in the future, the way you can analyze this decision-making process is based on this equation, but backwards. You can specify how much I'm expecting to earn, and then to get a better, a more standard framework on how to think of that money, you would convert it from a future value to a present value. And the connection between that is similar to this. It's saying that I'm going to apply some rate at which this decreases, like it discounts. Instead of growing with time, we're going backwards, that it's going to be less money now that gives you a bigger amount of money in the future. So it's the same equation to find the present value from a given future value at a given, instead of interest rate, discount rate. So that so you can write this equation for the net present value. And the reason why it's called net is because you're putting some money in now to get this future cash flow. And so the assumption is that net would be the case where it's more general, where it gives you the concept that you're putting in initial investment. So for one compounding period, if you only apply this discount once, you can write that the NPV equals some future value divided by 1 plus some discount rate. It's similar to interest rate. Could have the same number, but the concept is different, that you're going from the future to the present, divided by 1, because you're only doing this once. And we'll do a more general one where you can keep on having more periods that has this compounding effect, but in reverse. So this would be the net present value for one compounding period. This would be the future value. It's known, it's given, or you can play with that. And this is a concept called the discount rate. It's similar to interest. It's the same equation, same variable, but if you're going backwards, you think of it as a discount rate. And it's also known. So these two are known. And other names for discount rate could be called AKA cash flow. In the future, you can expect this cash flow, positive, or some net cash flow. And AKA the discount rate can also be called a rate of return. Okay, so that's a one compounding period, but in general, the net present value equals a sum of all the compounding periods. From 0, meaning when you first put up an initial payment, an initial investment, then each compounding period you have a certain cash flow, then you discount it by this discount rate raised to the exponent. So it's this equation in reverse, but over many compounding periods. And so the reason why, or what you do is, most of the time you say you apply a known cash flow, a known future value, and you apply a known discount rate. And so for a known cash flow and R, if that calculation results in a net present value greater than 0, then that means that it's a good move to do this initial investment and get these cash flows, and you'll be profitable after this period, after all these periods are compounded. And or you can do this so that you can compare different options, both in time and cash flows, to the present value, so that you can get a better idea how to compare apples and apples to decisions. So you can do this where bigger than 0 is good, of course. And if you want to compare different options, if you calculate the net present value of option A, and you calculate the net present value of option B, and option A is better, then you would choose bigger number. It has a bigger net present value, you would choose plan A. Okay, so we're going to apply this to a scenario and see what our different options are and calculate the net present values. Okay, so it's going to be a company, manufacturer that has $1 million, and the question would be how they use this $1 million. There will be an option of a no-risk investment. We talked about in class, no-risk investment means you lend the U.S. government money in the form of a U.S. Treasury, and that gains interest. And it's no risk because the U.S. government is stable. They have the biggest guns in the world, and there's not going to be any successful capital insurrections. So they're going to be able to pay you back by charging the taxpayers taxes to raise revenue. So that would be a low risk investment. The upside to doing that is no risk. The downside is that you don't gain much interest, and as we're going to see here, the net present value might not even be greater than 0. Okay, so then we're going to do another 3 different options. So plan A, it's going to be this no risk, 0 risk investment. Zero risk investment. 5 years interval. It's going to be a U.S. Treasury note, which is a medium-term time scale, which is 1% interest. So you give the government money, and they're going to pay you back this money at 1% interest after 5 years. Okay? Plan B, it's going to be riskier, but more juicy. So you're going to make stock investments. And it's going to be an 8% return, projected. And the problem is it's risky. It's risky because it's a stock market, and that's why we put a much bigger discount rate on there that we're going to apply both forward and backwards. But the projection is going to give you 8% return, but we don't know whether that's going to happen or not. And also, we're a manufacturer. Why do we even bother buying a factory if we can just make stock investments? So plan C will be you buy, you do your job, you manufacture or something, with a new machine. That machine costs $100,000, $100,000, $1 million capital cost. So you have to put in $1 million to get this new machine. But the projection is that you would get $25,000 monthly cash flow. $25,000 monthly cash flow after the machine. After you pay this initial investment. And that is risky because you don't know how accurate this monthly cash flow will be. It depends on a bunch of factors, of course. but this is our basis for the analysis. This is the numbers, the best numbers we have to play around with. And so the way that we're going to do this analysis is we're going to calculate the net present value of each of these options. So let's start with the most straightforward one. We have everything we need here. Oh, and I didn't mention here that the question is, this is also risky, so let's also apply an 8% discount rate to this option C, because it's going to be comparable to the stock market trade. And that's the thing about the discount rate, is that it depends on so many factors, and you can calculate it by some known financial accounting and business techniques. One of them is like taking the average. This is WACC. And the lowest discount rate that's typically possible will be for no risk. And this Treasury's rates are one solid basis to use. The smallest one will be a 1% discount rate. But in this case, so that's zero risk. But if we have this larger number, it kind of gives us some, there's the correlation between discount rate and risk is kind of a holy grail. Like if you can have some super accurate way to predict the future, that's basically what you're doing. If you're saying that you know the discount rate, which will for sure guarantee you to have a positive net present value, that's the same thing as saying that you can tell the future. So that doesn't exist, but you can use these numbers and some general experience, and 8% is a reasonable number. Okay, so for this Plan C analysis, we have everything we need to put a number on it. We know we're saying that we're going to have a monthly cash flow of $25,000. We know that it's monthly. We know that the discount rate is annual. We're saying that this is an annual discount rate. So let's do this analysis. So the question would be, the T rate is a 1% interest rate for the Treasury bond. This investment is expected to give an 8% return on our initial $1 million investment annually. It's risky. Similarly, any business operation is risky, so we'll put the similar discount rate on there annually. Okay? So let's do Plan C first. Okay, so we have this equation. But the question is, one first thing that we should remember is that if we are given a $25,000 monthly cash flow, that's a monthly cash flow, but the discount rate is annual. So you'll get a different number if you consider this cash flow like if you mix up this annual versus monthly. So there's two things we can do. We can convert this monthly cash flow to yearly cash flow, which would be 25,000 times 12, and then we can apply this 8%. What we're going to do is convert this 8% into a monthly rate, because so that's another way we can do it, and you'll get a different interest rate, because if you compound more quickly, you'll get a much different number unless you correct for this monthly versus annual. So the equation to do that, so for Plan C, the sub period, let's say that we're going to, instead of compounding annually, we'll compound monthly. Based on the known annual rate, it's the it's the interest rate of the annual, but you correct by the number of periods that you're going to break it down into. So starting with 0.08, so I'll go ahead and show the numbers. It's 1 plus 0.08 over 12, 1 over 12 minus 1. So now, instead of having 0.08 per year, it's going to be 0.0064 per month. So we're correcting for this compounding interest over the month. Then we can apply this to our equation. So for Plan C, and then 5 years is 60 months. So the net present value for Plan C is the time zero is you have to put in $1 million. So that would be $1 million outflow. The cash flow is out, so that's negative. And then the way that this math works, sub to the zero. So that this is 1. That there's no discounting effect because the exponent is 0. There's no time. Plus the cash flow after month 1. So it would be $25,000 plus 1 plus 0.0064 compounded over 1 month. Plus, you keep on going in the series. Now that we're out of the initial period and we assume it's the same cash flow, it compounds over 2 months. So then you would continue this pattern to the last month, the 60th month, which will be 5 years. And so what we noticed here, I didn't write it down, but over time, the $25,000 that you'll get in the future, the present value is less than $25,000. So this number is greater than 1. So you're dividing by a number greater than 1. So this number is the quotient. Dividing $25,000 by some number greater than 1 is going to give you a smaller amount. So the present value of $25,000 somewhere in the future is less than $25,000. So the question is, when you add up all of these cash flows over the compounding periods, is it bigger than the $1 million you put in at the beginning? So that's what we're doing. And when you plug in those numbers, after these 60 compounding periods, what I got was that the net present value is $241,123. So the good thing is greater than 0. So that's a viable option. Is that you're going to be, that's one way to say that you're going to be profitable at the end. Of course, it depends on your assumption of the discount rate, and it depends on whether these cash flows really do come in at this value, at this number. But based on this analysis, we can put a number on there, and we get a net present value for this plan, buying a machine. This machine is going to bring us $25,000 monthly cash flow. So that would be for plan C. Now let's talk about this so-called stock investment. So it's not based on monthly cash flows explicitly. What we're saying, it's basically mathematically the same thing as a loan, of course with more risk. It's not the same thing as a loan, but the numbers give you the same formula. So for plan B, the way to calculate putting in $1 million and buying stocks, and then after 5 years getting an 8% return, the way you find that number is the same way you calculate a loan, which would be the future value of this $1 million growing at 8% would be related to this discount rate, this return rate we said, raised to the compounding periods, which would be 5 annual increments. So it would be $1 million. So this is the annual, and there's less compounding periods because we didn't break it down into the months. So the future value of that would be $1,469,328. So that's the future value of Plan B, which is interesting because the net present value is this, but if you add that $1 million we put in, it's more than this plan. But it's not comparing apples to apples. This is more than $1 million in future dollars. This is with the equipment costs more than $1 million in present value. So let's put these on in terms of net present value. And it's not that straightforward to do that, but what we can do is assume that this is kind of like a loan. And let's do this monthly basis. Let's ask the question, if this were like a loan, I mean in terms of instead of compounding yearly, it'll compound monthly, and that would give us a monthly cash flow, an estimate of the monthly cash flow. So to do that, we would break this down. What we're saying is that we're going to get this amount, almost 1.5 million, after 5 years. Let's break it down into 60 months. And when we do that, we're going to discount it by a different, or give a different, the monthly rate. So the future value of B divided by 60 months equals $24. It's not a coincidence that we chose 25,000 here, because that's similar to what this cash flow of this yearly investment. So let's say we're going to assume this as the cash flow for option B monthly. So that basically gives us our answer right there. That in the same equation here, we're assuming the same discount rate, and we need to pay in the same initial $1 million to buy stocks or to buy the equipment. And based on this compounding interest, we'll have this amount, but if we divide it by some monthly payment, the cash flow that results is actually less than this $25,000 here. So just by comparing that, we can see that if you're going to have a higher cash flow with this option, you're going to have a higher net present value. And that's indeed the case. If we were to plug those numbers in, comparing apples to apples, the net present value of B is the negative $1 million to buy the stocks over 1, because this is raised to the 0. It's a negative. Plus, if this is our cash flow, so the subrate again. So we do this for the 60 months. And what I got was that so again, this is greater than 0, which is good, but according to this analysis, the net present value of Plan C is bigger than the net present value of Plan B. So that's interesting. Even though the future value is, the future value is higher than this, but and if you want to calculate the future value of Plan B, so Plan C, if we're saying that we're going to have $25,000 monthly cash flow, then the future value would just be, or future value, yeah. So future value of C would be 60 times $25,000. After you pay that $1 million, you're still going to have a net value of 1.5 million. So the future value is bigger. So both in the basis of a future value and a present value, Plan C is better. Okay, so I'll leave it for you guys, but if we were to do the same exercise for Plan A here, what you would get, the future value of Plan A, let's see, I'll write it right here. So Plan A is 0 risk, and you can find the future value of Plan A, which would be $1 million times a compounded interest over 5 years. And what you would get is, you'll make $50,000 at the end. Great. Okay, future value of A. So the future value is much less than this 1.5 million, much less than this 1.4, almost 1.5 million. So that's not as attractive. I guess what's attractive is that it's 0 risk. But the question is, if you were to divide this by 60, which I don't have, I don't think. Yeah, so divide by 60, 1,051 million divided by 60. So that would be cash flow of A. Is that right? Yeah, cash flow of A of $17,516 per month, if we're assuming a monthly. The question is, what is the net present value of A? I don't have the number, but I think it's negative. The question is the net present value of A even 0? I don't think it is. So even though you'll make some money on over 5 years, accounting for this discount of 1%, is it even worth it to do that? The criteria would be if it's greater than 0, you should move forward. That's just a general accepted standard analysis. And I'll leave it to you to apply this cash flow analysis for assuming this cash flow, and to see how that works out in terms of the net present value. Okay, so that's all I had. Thank you guys, and I'll see you next time. Okay.